Welcome, I am Alberto Gullino and this is my presentation for Electronics and Telecommunication Department PhD Poster Day 2021, dealing with multiscale and multiphysics modeling of VCSELs. My work is focused on 850 nanometers aluminum gallium arsenide oxide confined VCSELs, which are ideal for optical fiber coupling and show excellent dynamic properties alongside low production, testing and packaging cost. Therefore, they represent the state-of-the-art for short-range communication in data centers, so we want to improve their performances, in particular at the high temperatures reached in the server racks. For this reason, we need an efficient CAD approach to optimize them. To this purpose, we have reduced our in-house 3D physics-based VCSEL solver, Venus, to a one-dimensional solver called Diana, in which the electrical solver relies on a quantum-corrected drift diffusion model solved by means of Newton's scheme and the finite box method stabilized by means of the Scherfett-Langengammer method. The thermal solver deals with the static heat equation using a one-dimensional finite element method. These two are coupled self-consistently to a one-dimensional solver called VELM, which evaluates the optical modes and extracts the quantities needed to solve the photon rate equation. Since typically VCSEL modeling requires a three-dimensional solver, the first step of my work is the calibration of Diana on experimental results. This is obtained by starting from the parameters using Venus, and eventually the fitting accounts for the lateral effect, as shown by the optical power and by the wavelength as function of the flowing current. The calibrated Diana is an efficient tool to optimize the device under analysis. In the figures, two parameters are investigated at the critical temperature of 80 degrees Celsius, the cavity detuning and the number of pairs in the dBrs. From the first analysis, an optimal value of plus 15 nanometers is obtained. This value is then used to improve the dBrs, ending up with 5 pairs less in the bottom dBr and 2 less in the top one. Almost double the maximum optical power and later thermal rollover are obtained. However, this is not enough. Therefore, we want to try to solve the two main issues of the oxide-confined VCSELs. The first is related to the presence of the lossy p-doped top dBr, which introduces larger free carrier absorption losses and resistive losses. The second comes from the definition of accurate oxide aperture diameters by means of wet oxidation processes. Both could be addressed by introducing a barrier tunnel junction in the structure. This will realize all injection in the active region through tunneling across the VTJ, as depicted in the figure, here modeled by using a non-equilibrium Green's function approach NEGS. Thus, the top dBr will be end-doped, and a very accurate lateral confinement will be realized with photolithographic processes. From NEGS, a density current across the tunnel junction is extracted, and then used to compute a tunneling generation rate, which is then plugged alongside the generation recombination processes already included in the carrier continuity equations. Such an NEGS drift diffusion solver is then used to compare the LIV curves of the two devices. On the left-hand side, from the IV curves, one can notice that the TJ VCSEL provides smaller current values at equal applied bias, due to the additional voltage drop across the tunnel junction itself. The small electrical penalty is however largely compensated by the improved LIV curves on the right-hand side, that show larger maximum optical powers due to a reduction of the outcoupling losses, yet keeping fixed the threshold. Eventually, we also optimized the TJ VCSEL at 80 degrees Celsius. The cavity detuning is again set to the best value of plus 15 nanometers, and the optimal number of dBr pairs is extracted. In this way, when compared to the optimized oxide-confined VCSEL curve reported in a black dashed line, the maximum optical power increases by 30% and the threshold current reduces by 30%. The next step of my work will be focused toward the extension of this NEGS drift diffusion scheme also to Venus, our 3D fully comprehensive VCSEL solver. and towards the small signal analysis of these devices, which is crucial to fully evaluate their performances. Thank you for your attention.